Intrigued by our class discussion of anti-ballistic missiles, we set out to add intercepting functionality to our robot. In order to do this, we knew that we would need to both account for lag and predict future motion. We turned to the Kalman filter to anticipate the position of incoming projectiles. However, we found that the Kalman filter was unable to account for the two-wheel drive model of our robot. We therefore turned to the extended Kalman filter, which is built to handle nonlinear transition functions. Moving to the extended Kalman filter requires two changes from the vanilla Kalman filter. First, we replace the matrix f in the equation for mu t plus 1 with our nonlinear function little f. Then we substitute the Jacobian of little f, here marked as big F, into the equations for mu sub t plus 1 and k t plus 1. We then move to redefine our model using the robot's angular velocity. Using the robot's base velocity and angular velocity, we can calculate r, which is the radius of the circle around which the robot is traveling. For example, if the robot's right wheel had a velocity of 2 and the robot's left wheel a velocity of 1, the robot would travel around a circle with radius 3. Using these equations, we can solve for the angle of the circle that the robot has traveled. We then need to apply transformations from the robot's base coordinate system to the coordinate system in which this model applies. The three values in the top right corner of our matrix are our result. They are respectively the robot's x position, y position, and orientation. After all that, we are finally ready to define our transition function f. The first two subfunctions are simply the x position and y position functions that we defined earlier. Next, for the left and right wheel velocities, we use the basic Newtonian definition and give each wheel its own acceleration. We add in a constant acceleration assumption. And finally, we add the angular velocity defined definition of orientation. Now that we have defined our transition function, we need to solve for its Jacobian. The Jacobian is simply the matrix of partial derivatives, where a new function is differentiated in each row with respect to a different variable in each column. Given how messy the Jacobian is, we omitted it from this video. Now that we've found our inputs, we can use our Kalman filter to adjust for lag. We compared our lag time with the time required to communicate with the server, and defined our delta t such that lag was equal to 4 times delta t. In order to account for the fact that our position measurements are lagging behind our velocity measurements, we split our use of the Kalman filter into two parts. We saved velocity values that were 4 delta t old and combined them with our most recent orientation and position observation. We used these to keep our 4 delta t behind extended Kalman filter updated. The updated mu and sigma values that we obtained in this way are the ones that we saved from iteration to iteration. We then iterated through 4 more delta t's using our most current velocity values in order to remove lag. Finally, we extracted position and orientation from our mu t plus 1 in order to better calculate our attractive forces and our robot's need to turn. Here we contrast our pre-filter and post-filter response to attractive forces. Pre-filter, we were clunky and overcorrected. Post-filter, we turned the exact right amount. Here we contrast pre-filter and post-filter following of a moving goal. Pre-filter, post-filter. In general, the robot moves a lot more smoothly. Finally, we tackle our main objective. What our missile lacked in firepower, it made up for in style. In addition to correcting for lag, we used a regular Kalman filter to predict the missile's future position. Thanks to the extended Kalman filter, our robot positions itself perfectly relative to the missile's anticipated position.